All right, guys, it's time for fun with math. And today, what are we doing? We are going to talk more about finding Taylor series. So basically, the rest of this section is just how do you find Taylor series without using that definition. So that definition can be kind of tricky to use. And so we actually have five techniques or methods, if you like, to find Taylor series. One of them we've already done, which is the definition. And we kind of want to stay away from the definition if we can, because it's not the easiest one to use. But there are four other methods here. We have what's called the binomial theorem. We have integration, differentiation, and substitution. And these are just other ways to find a Taylor series for a function. So today, of course, we're going to talk about substitution. And let's just get into it because this actually goes really fast. So here are the standard Taylor series that we don't need to memorize. I'm going to give these Taylor series to you if you need them, but here are the standard ones right here. And so with these standard Taylor series, you can find a lot of the Taylor series of the functions that we often work with. So we've seen this type of Taylor series before. You can kind of think about it as a geometric series, but as a function. Here's a Taylor series for e to the x, and notice over here we have where x can be, so that's where the series actually converges. So for e to the x, you get an infinite interval of convergence, which is nice. Here's sine of x, and then cosine of x, and then tan inverse of x, ln of 1 plus x, and then finally down here, we have 1 plus x to the k, which is really a generalization of that function or that series there, if you think about it. This one's actually part of the binomial theorem. So this will be a special case that we look at next time. So what's the big idea? So what's the idea behind substitution? So let's just look at the problems we're going to do today. So what we want to do is we want to find the Taylor series of these three different functions, but we don't want to use the definition. What we want to do is we want to look at those standard Taylor series we were just talking about and somehow try to manipulate them algebraically to get them to look like this, basically, or like this, or like that. So we're going to use what's called substitution to find the Taylor series of each of the given functions, and we'll center them at 0, and then we'll also want to give their intervals of convergence. And remember, most of the time we'll find these Taylor series centered at 0, and then later in this lecture, I'll show you how you can find then the Taylor series that's not centered at 0, but using one that is centered at 0. So let's do this first example. And so here's our function right here. And the idea is, what does this one look like? So over here, what does this one look like over here? So where does it match up most likely? And so you can kind of see, like, it's definitely not this one, it's not this one, it's not this one, it's not this one, it's not this one, because you don't have any e's, sines, cosines, tan inverses, ln's, or any of that stuff. And so it turns out it looks most like this guy over here, which is really a subcase of this guy here when k equals negative 1. But we're going to use this top one. And so what we want to do is basically use this and do what's called substitution, right? So there's a little method of substitution when finding Taylor series. So, all you're going to do is this is like your unknown. So over here, that's like your unknown. So wherever you see your unknown, that's where you're going to put what I circled in yellow, basically. So I can rewrite this as being equal to the sum n equals 0 to infinity. And then right here, that's circled in yellow, I just replace it with the 2x. So I get 2x to the n. And then don't forget, over here, there's also an x. So I replace that with 2x. And so then 2x is an element of negative 1 to 1. And basically, you're done. I mean, almost. There's a little more math we have to do here, but that's basically it. And if I lost you there, guys, remember, this is just a note card. So on the other side of that circle is really an x, and on the other side of that circle, there's really an x. The problem we have is that you think the x on the back and the x on the front of the note card are the same x, and they're not. Okay, so you just turn it over. It's just a placeholder basically, and you have that thing on the other side. And so then all we have to do is define that Taylor series. So remember, for a Taylor series, you want this basically to look like, I don't know, some number c sub n times x to the n equals 0 to infinity. So what we want to do here is, 2x to the n is actually what? So sum n equals 0 to infinity of 2 to the n times x to the n. And then over here, that 2, you can actually divide out. So if you divide out here, you get x as an element and between -1/2 and 1/2. You don't have to write this out. I mean, you could write this out. So what does that really mean? That means -1 is less than 2x is less than 1. So if you divide everything by 2, you get -1/2 is less than x is less than 1/2. And you don't have to do this, but that's where this is coming from. You just divide by 2. It's fine. You're not going to make any mistakes there. But here's the fact. If you get a power series centered at 0 for this function, then it turns out that is the Taylor series. So this is a power series centered at 0, and it's equal to this function using this method of substitution, just plugging in basically. And so it must be the Taylor series for that function centered at 0. All right, and so that's it. That's all you have to do. Okay, let's do another example. So these are kind of nice, right? And so let's look at this guy right here. And so ask yourself, which series over here are you going to use? And hopefully you're like, well, there is a sign here, so I think I'll use this series for the Taylor series for sine. And you would be correct. And so this is going to equal what? This is going to be x times the sum, n equals, and you just come over here and copy it down. So 0 to infinity. And then this would be -1 to the n. And then you just have to be a little bit careful. So wherever you see an x here, you're going to place it with 3x. So we're going to get a 3x and then raised to what? The 2n plus 1. 2n plus 1. And then divided by here, 2n plus 1 factorial. And then don't forget over here, that x also becomes 3x. And so that works for 3x as an element of -infinity to infinity, right? So x lies between -infinity to infinity. And maybe I haven't used this symbol a lot, guys. So this means element of. Right, so usually I explain this as saying, here's a student is an element of this class. It just means they're in that thing. So it just means 3x lies between -infinity and infinity. Now, of course, we need to clean this up a little bit. And so this is going to be equal to, so we can multiply through by this x on the inside. And so we'll get sum, n equals 0 to infinity, -1 to the n. And then we have a 3x times, 3x to the 2n plus 1, and then all times an x. So you just bring that x on the inside, and then divide it by 2n plus 1 factorial. And then here, if you divide out by 3, you just get x lies still between -infinity to infinity, because, basically, if you divide this by 3, this by 3, and that by 3, you still get back -infinity and infinity. And we can clean this up a bit more. And so this is going to be equal to then the sum, n equals 0 to infinity, -1 to the n. And so this guy here, this is really a 3 to the 2n plus 1 times an x to the 2n plus 1. And so here we can write 3 to the 2n plus 1. And then don't forget, x to the 2n plus 1 and times another x, and that's x to the 1, is really x to the 2n plus 2. And then that's all divided by this 2n plus 1 factorial. And this is good for x between what? Between -infinity and infinity. And that's it, right? So there's really not much for us to do here. So there's our answer. So that's the Taylor series for this function, x sine of 3x. So nice and simple. No need to go back to that definition or anything. Okay, these can get a little bit more complicated though. So let's see one that's a little bit tricky. So again, we're going to use substitution. And so I want to look at this thing. And now when I look at this thing and I come over here and I'm trying to figure out which one to use, I kind of want to use two of them, right? Because I kind of want to use this guy here, but I also want to use this one here because it has an e to the x in it too. And so the trick is you're actually going to use both of them. So this is the same thing as what? This is the same thing as e to the x times a 1 over 1 minus x. And so what I'll do is I'll use the e to the x series there, and I'll use the 1 over 1 minus x series there. And so this will be equal to, and so I just plug in here for e to the x. It's a direct substitution. There's no, just x, right? So you don't actually have to change anything. So I just copy down this series here. And so at the sum, n equals 0 to infinity of x to the n over n factorial. And then I do the same thing here for this guy. Since the sum, n equals 0 to infinity. And then this is just x to the n. So I'm just copying down that series. And then where does your x live? Well, x is an element of, well, you have your one series here. And so that one, notice, goes between negative infinity to infinity. So it's negative infinity, infinity. But it's also in here. So then intersect with this guy here. And so negative 1 to 1. So this little symbol here means intersect. And you may think that's kind of weird. That's intersect. And the reason that's intersect is because this we use for union. And so the intersection, we just turn it upside down. So it's like union versus intersect. And so it's basically what they have in common. And so this tells me what x has to be between negative 1 and 1, because negative 1 and 1 is what they both have in common. All right, so now this one, if you had to multiply these all out, it might take you quite a bit of time. So here in this one, we just want to find the first 4 terms of the series. So I'm going to have you guys practice actually multiplying out an infinite series for the first 4 terms. So you basically want the 0 term, the degree 1 term, degree 2, degree 3 term. Those should be the first 4 terms. So let's just write this out. And so here, this series is actually, when you plug in 0, you get 1, and then plus x, then plus x squared over 2 factorial, and then that's just 2, and then plus x cubed over 3 factorial, which is 6, and then plus dot, dot, dot. I don't think I'm going to need any more terms than that. And then here, if I do, I'll have to go back and change this. Here, I can write out a few terms of this guy. So that's 1 plus x squared plus x cubed plus dot, dot, dot. And now I'm going to multiply out the first couple terms here. So the idea is you just, take the number 1 and you multiply it by all that. So that's going to be equal to, so 1 times 1 is 1. So I'm going to get 1. Then 1 times x is x. So I get x plus x squared plus x cubed plus dot, dot, dot. And then I'm going to do it again. So then I'm going to add, and I'm going to multiply this guy by everything. And so x times 1 is x, plus x times x is x squared, plus x times x squared is x cubed. And I think that's all I'm going to need, because again, I just want the first 4 terms. So it should be like the constant term, linear term, the quadratic, and cubic term, plus dot, dot, dot. And let's keep going. So now I'll multiply this guy by all these guys. And so then what do I get? So I get plus. And so x squared over 2 times 1 is x squared over 2. And then plus x squared times this guy right here would be an x cubed over 2. And then plus probably just dot, 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 because again, I only want those first 4 terms. And then finally, we'll multiply 1 time by this x cubed. So here I multiply this by 1, and I get x cubed over 6. And then plus, yeah, x cubed over 6 times x is x to the 4th over 6, but I don't really even need that. So I'm just put dot, dot, dot. And in that case, you might say, does it continue in that pattern, or are you just saying it continues? I'm just saying it continues. I'm not going to actually need that piece. And so now what do? I add like terms, right? So it's going to be equal to 1 plus, and I have an x plus another x. So I have 2 x's. And then plus, And then I have an x squared, and an x squared over 2. So that's 1 plus 1 plus a half. So I think that's 5 halves x squared. And then plus, what do I have left now? I have an x cubed, an x cubed, an x cubed over 2, and an x cubed over 6. I'm going to have to do some arithmetic. So 2x cubed plus x cubed over 2 plus x cubed over 6. Then, of course, plus dot, dot, dot. And so that's going to be equal to, I'm going to have to get a common denominator here. So I'm going to put a 6 down here and a 6 up here, a 3 down here and a 3 up there. And so what do I have? I have a 1 plus 2x plus 5 over 2x squared. And then plus, I got 12 of these guys, 3 of these guys. So what's that? 12 and 3 is 15, plus 1 more, so 16. So 12, 15, 16 over 6, x cubed, plus dot, dot, dot. Did I make any silly mistakes so far? Nope, we're doing great. This does reduce, and so that's going to be equal to 1 plus 2x plus 5 halves x squared plus 8 over 3 x cubed plus dot, dot, dot. And then don't forget, this is good for what? For x between -1 and 1. So that's a nice little problem there. And this actually tells me some interesting information. So remember, this is the Taylor series centered at 0 for this function. So I actually know something like this constant. It's on x cubed. So remember, for the Taylor series, this is actually what the third derivative evaluated at 0 divided by 3 factorial. I know that has to be equal to 8/3. And that comes right from the Taylor series formula. So what do I know? I actually know that the third derivative of the function at 0 is equal to 8 divided by 3 times 3 factorial. And if you think about that, that's just 8 over 3 times 6, which is just really 8 times 2, which equals 16. So this power series, the coefficients are actually telling me about the original function centered at 0 and the value of its derivatives, the value of the function and its derivatives there. So that's kind of interesting too. Okay. So now I did tell you we're going to do one problem where we find a Taylor series not centered at 0 and see how this works. So here's the problem we're going to do. And so here we're going to use the method of substitution again, which is kind of nice. And so the idea is you're going to look at this function and say, hey, over here, what does it look like? So here are our standard Taylor series, and which one does it look like most? And you guessed it, it's just the top one. It looks a lot like that one. And of course, process of elimination is great. X, 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 X. And then you might say, oh, well, it kind of looks like that one. And it does, because remember, this is a special case. K equals -1. That is actually that formula. All right, so what's our job? Our job is to take this thing and try to turn it into this thing. And when I say this thing, I mean it's like 1 over 1 minus something. I'll just put a circle. Let's put a little square there, right? So I'll put a little square there because I know this is going to be equal to the sum n equals 0 to infinity of square to the n, as long as square lies between what? As long as square lies between -1 and 1. Right? So this is like a template, basically, right? These little formulas you can use. This power of substitutions, basically algebra, is what we're putting down here. Okay, so I'm gonna turn it into it. It's really not that hard to do. So the first step might be just to write this as 3 times 1 over 1 plus 5x. Now I got the 1 on top. So it's like match, match. All right, now I have a minus sign here. And so I need to get a minus sign there. So how am I going to get a minus sign right there? Well, that's not too bad either, because it's going to be equal to 3, 1 divided by, and then I have 1 and then minus, and then I can put a -5x. Oh, I forgot what I was doing. I'm sorry. I need to get this centered at 2. So I was doing this centered at 0. So let's go backwards. Let me go back here. So that changes the game just a little bit, not a ton. So we can do this. Start here. This is fine. But centered at 2, what do you want to do? You want to make that x become an x minus 2. And it's not hard to do. So check it out. This is going to be equal to 3, and I have a 1 on top, 1 plus 5. And let's turn this x into an x minus 2, because that's when it's centered at 2. And so what I'm going to write is x minus 2. And then I put a plus 2 right next to it. Now notice, I didn't change anything. It looks different, but minus 2 plus 2 is really adding 0. But now I have something with an x minus 2 into it. And so if I can turn that into this guy over here and replace my x's with x minus 2's, I should get a power series centered at 2. So this is going to be equal to then, we have a 3 and then a 1 over 1 plus. I'm going to keep those x minus 2's together. So I have a 5 times x minus 2. And then 5 times 2 is a plus 10. And so what I really have here is a 3 and a 1 over, and then 10 plus 1 is 11. So 11 plus 5 times x minus 2. So that was my first goal there, basically, to get an x minus 2 in there. And again, that x minus 2 is always going to stay together because that's going to be my substitution in the end. And now I'm trying to get it to look just like that guy right there. And so now, how can I do that? Well, I need a 1. So I need to somehow turn that into a 1. So guess what I'm going to do? I'm going to factor it out. I'm going to pull that 11 out, like when I pull that rabbit out of a hat. So I have 1, oops, let's give myself a little more space. So 1 divided by, I have a 3, and I'm going to pull out 11. On the bottom, this will be a 1 plus, and then this will still be 5 times x minus 2, but now I'm going to divide it all by 11. And so notice I just pulled out 11, and so if you multiply through, you just get this back. But now I have a 1 there, which matches up with that guy right there. And then I need to turn the plus into a minus. So let's do that. So that's going to be equal to, and so this is 311, 3/11ths, and then times, and I have 1 over 1 minus, and I'll write this as negative 5 x minus 2, all divided by 11. And now I got it. So I can make my substitution. So I'll take this guy here, and I'll plug it in for x. Wherever I see an x, I just replace it with what's written right there. And so this will be equal to, let me just move this up just a little bit, give us a little more room. And so this will be equal to 3 over 11, and then times the sum, n equals 0 to infinity of what? So wherever you see an x, you're going to replace it with this negative 5, so negative 5, x minus 2, all divided by 11, and everything is raised to the nth power. And this is for what? Negative 5, x minus 2, divided by 11 is between, so it's an element of this interval negative 1 to 1. And again, all I'm doing is coming up here, and if you plug that in right there, you get back this thing, and then you plug it in here, that's the series, and you plug it in over here, and that's where it converges. Now we have to simplify this. So let's simplify it a little bit. So it's going to be equal to 3 over 11, the sum, n equals 0 to infinity, and we have negative 1 to the n. We have a 5 to the n. No, that looks like a 6. Let's change that. We have a 5 to the n. We have an x minus 2 to the n. And this is then going to be divided by 11 to the n. And then this is going to be good for what? So over here, we can do a little bit of the arithmetic, basically. And we don't have to write it as an inequality because nothing's going to really change here. So we're going to multiply both sides by 11. And so this tells me what? Negative 5 x minus 2 is an element of, and then this is negative 11 to 11. And then we're going to divide out by negative 5. But because these numbers are the same, you don't have to flip-flop or anything like that. So you're going to get x minus 2 is an element of, and it's going to be negative 11 over 5 and 11 over 5. And then finally, we're just going to add 2 to everything. So add 2 here and add 2 there. And so then x is going to be between what? So if you add 2 to negative 11 over 5, so that's adding 10 over 5, so that's like negative 1/5. And then 10 over 5, this one's 21 over 5. And so this is good for what? For x between, so an element of negative 1/5 to 21 over 5. And then we do have this 3/11ths right here, so I guess we should push it in on the inside. So it's a sum, n equals 0 to infinity, -1 to the n, 3 times 5 to the n, and then divided by, and so here you could put 11 to the n plus 1, because you're multiplying 11 times 11 to the n. And then if you want, you could write this as x minus 2 to the nth. You could pull it out of that fraction if you want to. And then this is good for, of course, this x is an element of the interval negative 1/5 to 21 over 5. And when you use substitution, you don't have to check the endpoints. They always stay the way that they are. So there's my answer. So that's kind of cool. It's a nice little way to find Taylor series centered someplace that's not 0. If you know what it is at 0, you can kind of move it around by using this little trick that's doing algebra. And so what's the trick? So let me come back here, because at the beginning, I kind of got us off to a little rough start. But the trick is basically getting the x minus 2 in there. Because it's centered at 2, I try to get an x minus 2 in there. And the trick is just put it in there so that x becomes x minus 2 plus 2. And you just put that in there. And then you keep that x minus 2 together always and try to turn it into that form, that form right there. And once you got that, you're good to go. You can use the substitution and get your answer. All right, so that's all I have for you guys today. So go have fun with math.